In a previous lesson, you learned to differentiate composite functions by using the general power rule for derivatives, the chain rule for power functions. So the derivative of u to the n with respect to x is n times u to the n minus 1 times u prime. For integration, we reverse this process. To integrate, u prime must be part of the integrand in order for us to use general power rule for integration. Begin by differentiating this first problem and then check your work. Here's our derivative. Before we can use the general power rule for integrals, we must make sure that u prime, the derivative of that inside function, is present in the integrand. U is the function of x being put to the power n. U prime must be present. Are u and u prime in our integrand? Yes, they are. Only once I've established that u prime is also in the integrand can I integrate using this formula. You can always check by deriving the answer you got for your integral and seeing if it gives us the original integrand. Pop down, power down, times derivative of the inside. So yeah, this is what we started off with, our integrand. Note that the derivative of the inside of the power function must be present to integrate. We have a function of x to a power n. U is our function of x, making u prime 3. Is 3 a part of our integrand? No, it's not. But guess what? I can actually manipulate this algebraically so that u prime is in the integrand. U prime is 3. That needs to be in the integrand. I can't just multiply a 3 by the integrand. I can only multiply something by 1 and it still be unchanged. So guess what? I'm going to multiply by 1/3 times 3 because that's a special form of the number 1. And then I'm going to take 1/3 and say, I don't need that as a part of my integrand. Now, is u prime present in our integrand so that we can use the general power rule for integration? Yes, it is. U to the n plus 1 over n plus 1. And you'll multiply that 1/3 to get your final answer. For number 4, I don't actually see a function of t that is to a power, so I could technically expand and then just use power rule for integration. But if you notice, this is the derivative of this. So if u is t cubed plus t squared, then u prime is 3t squared plus 2t, which means u to the power of 1 and u prime are all in the integrand. So I can simply use our formula for integration. U is t cubed plus t squared to the power of 1 plus 1 over 1 plus 1 plus c. There's the answer for our integral. First of all, to use the general power rule for integration, I would like it to be written as a power. So I'm going to rewrite the radical that's in the denominator as this quantity to the power of negative 1/2 in the numerator. Now I have a function of x that is to the power of n, so that will be u, and u prime will be 12x squared. Now, is this 12x squared? No. We can multiply by a special form of the number 1 in order to make this have u prime in the integrand. To make the 6x squared 12x squared, I need to multiply by 2. If I multiply this integrand by 2, I'm going to multiply outside of the integrand by 1/2. Now I'm just multiplying the whole integrand by a special form of the number 1, but taking out the 1/2 and keeping the 2 inside. This is an equivalent integral to the one you see above. Now we can use the general power rule for integration. Your function can be written as a rational exponent or a radical. It looks like our function u to the n is y cubed plus 1. 3y squared plus 0. Okay, if I needed to put a 3 in here, I could do that. I cannot put a variable into an integrand. You can only multiply by a constant. This is the scalar multiple of an integrand, being able to take some numbers out of an integrand if they're a product. So I can't use general power rule for this, but I could expand it since this is just to the 2. And then I can just integrate by a power rule for integration. And here's our result. For more complicated integration problems, simple rules of integration might fail because integrating is definitely harder than differentiating. So a special type of integration technique is called U-Substitution. U-Substitution is not what we did here. This was reverse chain rule or general power rule. A common substitution will be to let u equal the radicand. You should use this method of substitution only when the simpler methods don't work. This is a method of last resort. Don't use U-Substitution unless you absolutely have to. Often let u be the radicand. Solve for x in terms of u, differentiate the equation from step 2, and then find dx. Substitute u expressions for x expressions in the integral. Most often, dx does not equal du, so don't forget to substitute for dx. Then integrate and then substitute back so your final answer is in terms of x. What? Okay, so what we're going to do is we're going to choose the radicand to be u, since that is the most common substitution we make. So instead of writing u prime, I'm going to write du over dx, and I'll show you why in a second. Du over dx, so the derivative of u with respect to x, is equal to 1. This du over dx notation was created by a mathematician named Leibniz. And it's so crazy cool because not only is this a notation that tells us derivative of u with respect to x, but we can actually treat this notation kind of like a fraction. We can use inverse operations to separate the du from being over the dx. Now du is equal to 1 times dx. Again, they said most often it doesn't equal, but it does for us. So du is equal to dx in this case. Then they said to solve for x in terms of u. So if I took this equation, x is equal to u plus 1. It looks like I did steps 3 and 4 before step 2, but that's all right. Now we're going to substitute the u expressions for the x expressions. X can be rewritten as u plus 1. Square root x minus 1 can be written as square root u. dx in this case is actually equal to du, so I will replace it with du. That way all my variables match. You can't have some u's and some x's. Everything needs to match. Once I've substituted u, I can do some algebra to simplify this integrand by distributing the u to the 1/2. And now I can just use the power rule for integration. This is our answer, but this is our answer in terms of u, and the original function they wanted us to integrate was in terms of x. So now we're going to substitute back in our x expressions for the u's. There is the answer for our integral. Again, for u substitution, oftentimes the radicand should be selected as u. Du over dx is 2. When you multiply both sides by dx, du is equal to 2 times dx. If I were to solve for x in terms of u, I would get 1/2 u minus 3/2. It is helpful to write this as a product with negative exponents. And now I'm going to substitute all the u stuff that I figured out instead of the x's. Now 2x plus 3 is u. And dx is equal to, oh, what is dx equal to? Dx is equal to 1/2 du. And I'm plugging into dx, so I need to replace it with 1/2 du. We've changed our integrand to be all in terms of u. Let's clean it up so that we can integrate. Well, now we just have the sum or difference of two powers, so we can just use the power rule for integration. We've integrated, so we just need to plug in u to leave our answer entirely in terms of x.